In this video, we'll look at forces acting on objects on inclines and look at how Newton's laws are applied on angled surfaces. Consider a skier sliding down a ski slope. While snow is slippery, there is still some friction there between the snow and the bottom of the ski, even if the ski is well waxed. The coefficient of friction of snow varies depending on the type of snow. For example, wet snow will have more friction than dry snow, and icy snow will have more friction than powder snow. Now let's look at all the forces and consider how many forces are there acting on the skier. The first obvious force that is acting is the force of gravity. As gravity acts directly downwards, the direction of this force, which is the weight of the skier including his skis, is vertically down. As the skier is in contact with and sliding along the snowy surface, he is not sinking into the snow, then the surface must be pushing back on the skier via the normal force. The normal force vector is always directed perpendicular to the surface. And finally, we have friction trying to oppose the motion of the skier sliding down the slope. So the direction of the frictional force is directed up the slope against the motion. So there are three forces in total acting on the skier. We can see that two of the three forces are not aligned in the horizontal or vertical direction, but at some angle. The frictional force is directed at the same angle as the slope, and the normal force is directed at an angle that is normal to the slope. Since the ski is sliding down the slope, then it is convenient to define the coordinate system in the same plane as the slope and define going down the slope as a positive x direction, which means the direction perpendicular to the slope will be the y direction. So friction will point in the negative x direction, the normal force will point in the positive y direction, and the skier will accelerate in the positive x direction down the slope. But what is causing the skier to slide down the slope? Intuitively, we know that this is gravity. But in our force diagram though, gravity is pointing directly downwards. To understand the force that is causing the skier to slide down the hill, we need to resolve the gravity force, or the weight, along our coordinate system. We can see that the gravity vector has a component in the positive x direction, which we'll call wx, and a component in the negative y direction, which we'll call wy. Now that all of the forces have been resolved along our coordinate system, we can write out the force equations for them. Let's start with the y direction. The forces in the y direction are the normal force pointing in the positive y direction and the component of the weight pointing in the negative y direction. Along the y direction, the net force is equal to 0 because the skier is not in motion in this direction. So the normal force is equal to the component of the weight in the y direction. Since the weight is equal to the mass times acceleration due to gravity, then the weight in the y direction is equal to mass times the component of gravity in the y direction. And of course, the y component of gravity is equal to the cosine of gravity. Now for the x direction. Along the x direction, there is the x component of the weight in the positive x direction. Opposing that is a frictional force in the negative y direction. And if the weight along the x direction is greater than the frictional force, then there will be a net force in the positive x direction, giving us acceleration down the slope. Now, the frictional force is equal to the coefficient of kinetic friction, because the ski is moving, multiplied by the normal force. And we've already established that the normal force is equal to mg cos theta. We can also write the weight in the x direction as a mass times the component of gravity in the x direction. And the component of gravity in the x direction is equal to the sine of gravity. What we notice in this equation is that mass appears as a common factor. So we can cancel mass out, and we end up with the equation for acceleration, which says that the acceleration due to gravity down the incline minus the acceleration due to friction up the incline will give us the net acceleration down the incline. Remember that friction is a reactionary force and will never be greater than the force that it is opposing. So friction will never pull the skier up the hill, but only tries to slow the skier down the hill. Let's now have a look at the influence of the slope angle on this equation. If the angle of the slope is large, e.g. if the slope is steep, do we expect the skier to accelerate more or less? If we increase the angle, then sine theta gets larger and the component of gravity in the x direction increases. At the same time, the normal force gets smaller because cos theta gets smaller with increasing angles, so the frictional force decreases. The net result is greater acceleration down the hill. Conversely, if the angle decreases and the slope is flatter, then the normal force increases, so friction increases, while there is less gravity along the direction of the slope to pull the skier down. The following graph shows the dependence of the net acceleration as a function of the slope angle for a surface with a coefficient of kinetic friction of 0.05. What it shows is that at an angle of less than 3 degrees, there is enough frictional force to prevent the skier from sliding. Above 3 degrees, the frictional force is less than the force of gravity along the slope and the skier will slide. As the angle increases above 3 degrees, the acceleration increases. When the angle is 90 degrees, this basically means that there is no slope and the skier is in free fall, so we experience the maximum acceleration due to gravity, which is 9.8 meters per second squared. So, for the final quiz in this video, using the equation that you have derived for acceleration, what is the acceleration of the skier going down a 30-degree slope with a coefficient of kinetic friction being 0.05?